Our final presentation today is BlueFlow.
Imagine turning on your faucet and not realizing that inside the pipes beneath your city, an invisible problem is already costing millions of dollars. Over time, biofilm and corrosion build up along pipe walls, increasing friction and forcing pumps to work harder just to move water. In some systems, this means 30% of treated water is lost before reaching consumers. Not only that, but biofilm growth also leads to numerous health consequences, including respiratory and systemic illnesses. Unit facilities then spend significant amounts of money on energy, maintenance, and pipe replacement. As populations grow and water infrastructure ages, cities need solutions that are not only effective, but also scalable, affordable, and long-lasting.
Current solutions mainly treat the symptoms instead of the source of the problem. Chemical disinfectants like chlorine require constant monitoring and can negatively impact the environment. Mechanical pipe cleaning is expensive and labor-intensive, while many antimicrobial coatings lose effectiveness over time. Other technologies may reduce friction or corrosion, but very few target both energy efficiency and biofilm prevention directly at the pipe surface, where the problem actually begins.
And so that's where SharkPipe comes in. SharkPipe is a modified PVC water pipe designed to reduce energy loss and prevent biofilm buildup by engineering the inner surface of the pipe at the micro and nano scale. Instead of leaving the interior smooth like traditional systems, SharkPipe uses a combination of shark skin-inspired riblet microstructures, as you see here, with integrated Zwitterionic polymer technology to improve flow and keep the pipe clean over time. The inside surface of SharkPipe contains microscopic riblets inspired by shark skin. These grooves are aligned with water flow and reduce drag by reorganizing the turbulence that occurs near the pipe wall. This means that pumps then use less energy to move the same amount of water. In addition to these riblets, SharkPipe incorporates Zwitterionic polymer technology directly into the pipe material rather than relying on a temporary surface coating. During production, these amphiphilic molecules naturally migrate toward the pipe's inner surface, forming a thin nanoscale hydration layer that strongly binds water molecules. Research has shown that this hydration barrier can cause a 90% reduction in bacterial adhesion. And importantly, SharkPipe does not sterilize water or replace disinfectants. Instead, it creates a pipe surface that is less favorable for microbial growth, supporting existing treatment systems in a completely passive way.
One of SharkPipe's greatest strengths is that it both improves flow efficiency and long-term resistance to biofilm. Unlike traditional pipes that gradually lose efficiency as they age, SharkPipe maintains its performance from day one by reducing drag and preventing buildup. Another major advantage is that SharkPipe is fully compatible with existing municipal materials and manufacturing methods. The pipe uses standard UPVC, and the riblets are formed through microstructured extrusion, a scalable process already used in the industry. Additionally, the Zwitterionic additives are blended directly into the PVC, meaning that the anti-fouling function is permanent, not a coating that wears off. Together, these features make SharkPipe practical to manufacture, easy to integrate, and capable of delivering long-term savings through lower pumping energy, reduced maintenance, and extended pipe lifespan.
Financially, SharkPipe is designed as a long-term infrastructure investment. Our projected manufacturing cost ranges from about $6 to $44 per foot, depending on pipe diameter, and sells for about an average of $35 per foot in early pilot programs, resulting in a profit of $13. During our initial pilot run in year 3, and assuming we sell 5,000 feet worth of SharkPipe, this translates to approximately $175,000 in revenue and $65,000 in gross profit our first year. The opportunity here is enormous. The global water and wastewater pipe infrastructure market is currently valued at roughly $30 to $36 billion and continues to grow as aging systems require rehabilitation. Our initial obtainable market of $20 to $30 million represents a realistic portion of this, giving us a strong foundation with room to scale.
Our 5-year plan begins with research, prototyping, and material optimization during the first 2 years. We will be focusing on finalizing, then validating the performance of factors such as riblet geometries and the Zwitterionic PVC blend. By year 3, we begin pilot-scale manufacturing and controlled field testing in municipal and campus systems. Years 4 and 5 will focus on NSF ANSI certification, scaling at manufacturing, and full commercial deployment. To support this process, we are seeking $1.1 to $1.3 million in early-stage funding through SBIR grants, NSF innovation programs, and private partnerships to complete research, prototyping, and commercialization.
Ultimately, our design helps reduce pumping energy, lowers maintenance from buildup inside pipes, and allows water to move more smoothly and efficiently through the system. Most importantly, SharkPipe addresses a global growing global infrastructure problem in a way that is scalable, realistic, and scientifically grounded. So today we invite you to envision the future of water infrastructure with SharkPipe. Thank you.
Very nice presentation. I think you've taken two really good ideas, both controlling the surface and then using Zwitterions. However, you need to convince me that you can actually manufacture this at scale. So tell me how you would start with the shark skin. How would you make that?
Yeah, let me, we have a few extra slides to kind of help you better visualize this. Okay, so I'll start with the Zwitterions first, actually, just because that's incorporated into the PVC. So we would first create sort of like a master batch blend. So we would combine the Zwitterions with the PVC. And then in order to create that sort of shark riblet structure, we undergo a process called microstructure digeometry extrusion. And essentially, we're taking this hot PVC with the Zwitterions embedded into it, and we put it through this extrusion mold to where it'll embed these riblets in the interior of the pipe. And then after that happens, we then perform surface segregation. So essentially what we're doing is we're running water through the pipe, and these Zwitterions, they are polar, right? And water is also polar. So these amphiphilic molecules will then migrate towards the inner surface of the pipe, kind of allowing these Zwitterions to be more effective in that sense.
So is there going to be Zwitterions throughout the thickness of the pipe, not just on the surface?
It's primarily, so we do that water step here to kind of bring these Zwitterions towards the innermost part of the surface, so that when water is actually, going through it, it'll create that hydration barrier.
So they're going to migrate after you make the pipe?
Yeah, like, do you want to explain it?
So you make the pipe first with the riblet structure, and then the Zwitterions are added.
This is, sorry, go ahead.
Go ahead. Yeah.
Oh, sorry, this was a little bit backwards. This was like slightly outdated, but we create the blend first, then put it through the extrusion, and then from then on, in the last step, the Zwitterions will migrate.
Okay.
Sorry for the confusion.
Yeah. Thank you.
Impressive. So how did you guys decide on this? This is kind of an expansive vision on something that's needed throughout our country, throughout the world, really. It seems like would be a lot of financial and community, city councils to replace these pipes and things. So anyway, how did you get drawn to this, aside from that?
Yeah, so first starting off with the science part of it, we are part of our school's ACEP program, which stands for Advanced Science and Engineering Program. And in our sophomore year, we took a bioengineering class where we learned about many different things, but specifically biomimicry was the one topic that stood out to us. And this helped inspire a few different projects. One of them we did last year, hydrospides, and this year we advanced into SharkPipe, where we stayed in the water industry, and we wanted to just help evolve with that and sort of incorporate shark skin riblets and all of that into creating this product.
Great presentation. I want to ask about your defensibility at scale. So what stops a large pipe manufacturing company, right, from adopting this technology? Is it a system of patents, exclusive contracts? How are you guys thinking about navigating that?
I'm sorry, I don't think we really understand the question. Would you mind explaining a little bit?
Yeah, so, I mean, your technology seems very sound, right, comprehensive, but, you're going against incumbents that have billions to play around with, right? And so, inevitably, if you don't have a strong moat for defense, right, they'll just, copy it, or they'll, a good outcome is they buy you, right? But, so what's your path to defensibility, I guess?
I guess first and foremost, like filing for patents. I think we included that somewhere in our business plan, but that is probably the first way we would provide defensibility for our own product. And then in terms of why companies would want to invest in this, so just a brief cost analysis compared to normal PVC pipes. Although ours does cost approximately 15 to 30% more to sell. We do offer a 6% reduction in energy loss and also a 90% reduction in biofilm formation. And so with that, over time, these companies will not have to, maintain these pipes, which are very, very costly processes.
Cool, thank you.
I really don't have any questions other than why is there such a large variability in the manufacturing costs?
Yeah, that's a fantastic question. So our plan is to target municipal pipes, and so there are a variety of sizes, right? So our goal is to target or create, pipes that are about 6 inches in diameter to 16 inches, and that is a large range. So we do have, ranges and prices for that as well.
I just want to conclude by saying I almost beat the gong that time.
Thank you.
Thank you.